So I guess I'll start now. Let's, I guess I'll start now. This might So today we are going to talk about I'm having some technology issues again. Please don't call me a boomer again. But yeah.
I was about to type that. Sad.
Okay, I figured out what's going on.
When will we start?
When I figure out all my technology.
Ritam, I guess your screen isn't visible. रितम भैया की वॉइस भी नहीं आ रही है.
Yeah, so we can discuss that. Let me open GeoGebra. We were till
Wait, what's going on?
We are discussing a problem we didn't solve in RG's lecture
Yeah,
till the time we are
I'm the one
fixing.
talking. I'm the one talking. I'm RG.
ओ अच्छा 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 मुझे पता नहीं था तो फिर
Yeah.
हम वो आपके लेक्चर वाली प्रॉब्लम डिस्कस कर रहे हैं.
Okay. Enjoy.
आपके कुछ आइडियाज हैं मतलब या फिर आप स्क्रीन शेयर करना चाहोगे?
नहीं, मैं अपना कुछ और कर रहा हूँ.
ठीक है. Yes, so I think the main problem was if we have some edge connecting like A to D. कलर कर देता हूँ ताकि पता है. So I think main problem was when we, if there is some edge going out there, it was not a problem. I think the main problem was then when there is some edge A to D. But I think we can handle that because here this edge includes degree of both A and D. So I think this shade is handleable. What is others ideas? Any opinion? Should we discuss the problem?
Please explain the problem.
Who is asking? It is China TST.
Yeah, China TST 2015 P3. Okay.
I will just show.
It was being discussed in RG's class. Like,
Yeah, I
उसके
wasn't there
बाद
then. I'll find the problem.
This. Let's focus on problem. Any should we discuss it or
What have you people done so far on it?
are you Pranjal?
No, no.
Actually, it was a problem. Like this is the problem. Uh,
This
uh,
is Atul. I'm sure he knows.
do you know the problem?
What the problem now? Like, I'm looking at it now.
P3.
Yeah. So basically, till now we have the answer is 3kn. We RG told us that the answer is 3kn. We have found a construction for it.
I see.
Answer is 3kn. We have found a construction for it. Now we are just proving that this is the maximum possible, and we are basically restating. We have just restated the problem in terms of graph theory. Nothing more.
I see.
I think we are not too far from the solution because many
Arjun,
things. हाँ
like इसमें कि ग्राफ वाले पार्ट में क्या प्रोग्रेस होता है, can't recall that. Am I going
ग्राफ
to like I think if you prove that 3k n plus 1 is not possible, we are done for 3k n plus 2 obviously by the similar argument.
नहीं नहीं हमें 3k n+1 ही प्रूव करने हैं.
So what was the
ऐसा
argument in this? As of now, like, I can't recall that.
वही तो सोच रहे हैं. बस अभी तक हमारी इस ग्राफ थ्योरी वाले में तो एक ही प्रोग्रेस थी कि ए और बी दोनों से नहीं निकल सकती, मतलब आई और जे, वरना हम ए बी को ए जी और बी आई से रिप्लेस कर देंगे तो एक एक्स्ट्रा मैचिंग मिल जाएगी और हम मैक्सिमल मैचिंग
Yes,
देख रहे हैं.
yes, if we go AS, okay, okay, yes, fine.
मेन प्रॉब्लम बस यही है कि अभी अगर ये बी बी के यहाँ से आई जा रहे हैं और ए डी से कनेक्ट हो रहे हैं, लेकिन वो इतनी बड़ी प्रॉब्लम नहीं लग रही क्योंकि ए और डी की डिग्री दोनों वेस्ट हो रही है इसमें.
They have maximum degree as 20. Oh, also, Atul, if you don't know, the graph is कि जो vertex है हमारे, they are the Isenka flavor. Yeah, I guess it is color. So the vertices are color, and the edges are, suppose a kid buys the candy of color A and color B. So we connect A and B. So there can be multiple edges between two vertices. This is the graph.
I see.
I think we can denote by small p degree of a capital P.
Yes.
I think shouldn't be too hard. So we can like consider several cases on them maybe. Like if I assume we can basically there are two cases, either A will be connected to I or A will not be. लाइक बी से यहाँ से कुछ निकल रहे होंगे, अब ए शायद आई से कनेक्टेड हो, कुछ शायद यहाँ नीचे जी एच में ना हो, ऐसे ऐसे केसेस होंगे. तो तो फिर अब
Maybe let's just analyze first the case k equal to 1 and prove 3n plus 1 is not there. Maybe that would mean something.
अच्छा आप k इक्वल 1 के लिए कह रहे हो. हाँ k इक्वल 1 को एनालाइज करते हैं तो फिर हमें बस ये ए बी वाला पार्ट देखें. हाँ लेकिन वो केस तो हम सॉल्व ऑलरेडी कर चुके हैं ना, क्लास में हमने देखा था. मेन प्रॉब्लम तब आ रही है हमें जब ए डी से कनेक्ट हो रहा है, बाकी सब तो हमने क्लास में कर ही लिया था. Oh, but this is not possible if A is connected to I, J और K तो निकल ही नहीं सकते ना बाहर, वो तो क्लास में डिस्कस.
J and K also, like why can't be there A, B and C, D in the k equal to 1 case? What's the problem with that?
अच्छा
There can be.
ये जो स्ट्रगल है ये 1 घंटा वही उसी समय से चल रहा है.
यार टफ प्रॉब्लम्स पे तो हाँ चलता ही है.
नहीं मैं हाँ मतलब उस समय से कंटिन्यू है.
हाँ उसी का कंटिन्यू है, हमने पूरा सॉल्व नहीं किया था तो कोशिश कर रहे हैं कर लें.
और वो जो क्लास था वेक्टर स्पेस का,
वो कुछ टेक्निकल इश्यूज हैं तो जब तक फिक्स हो रहे हैं हम तब तक टाइम यूटिलाइज कर लेते हैं.
ओके.
तो यहाँ से फिर दूसरा केस है, यहाँ से शायद एच से कुछ ऐसे ऐसे निकल रहे हो, तो बस इन्हें ही हैंडल करना है.
Like in the 3n, basically these are the flavors, no? So there is not necessarily A, B ही होगा. There can be multiple also, like there can be a pairing with 3 colors also. Yes, in A equal to 1 case. Like it is not
ये
necessarily.
डिग्री ऑफ एज ए बी तो लेस देन इक्वल टू ए बी प्लस बी आई प्लस ए आई. ये सारी डिग्रीज हैं यार, तो ए प्लस बी प्लस आई बाई 2. हाँ पर अब ए टू डी को भी हैंडल कर लेना ये इतना मुश्किल तो नहीं है. हाँ ऐसे कर सकते हैं कि हम ए डी की डिग्री अगर हाँ मेरे हिसाब से ये सही, ये गलत मेथड है. हमें शायद ऐसे लिखना होगा कि डिग्री ऑफ ए नहीं, हाँ ऐसे 2n is greater than equal to degree of a capital A, which is greater than equal to ये AI का डिग्री प्लस ये, अरे क्या कर रहा हूँ, प्लस ये BA का डिग्री, मतलब नहीं, प्लस ये AB का डिग्री प्लस ये AD का डिग्री। ये तो ठीक लग रहा है ना सबको? मुझे तो ठीक ही लग रहा है ना? सिमिलरली ये H का भी अगर मैं यहाँ कर दूँ तो 2n इज ग्रेटर देन इक्वल टू ये बड़े H का डिग्री विच इज ग्रेटर देन इक्वल टू ये
Why
वही,
can't be there any other like A से J पे जाता हुआ?
वो उसका तो हमने कंट्रडिक्शन कर दिया था ना प्रूव। अगर A से कोई J जा रहा होगा तो AB को BI और AJ से रिप्लेस कर देंगे तो कंट्रडिक्शन आ जाएगा।
And what if there is no such I, only AJ?
दोबारा कहना।
Suppose कोई I नहीं है हमारे पास, like just hide I भी I once.
हाँ मैं आपकी बात समझ गया, लेकिन B से निकले A से निकले सिमेट्रिक ही है ना, तो ज़्यादा मैटर नहीं करता शायद। मैं हाइड कर देता हूँ पर आप हाइड करूँ क्या?
नहीं ठीक है, I have got it.
HK plus HM। आई थिंक प्रॉब्लम ऑलमोस्ट सॉल्व ही है। अभी नहीं, अगर हम ढंग से ऐड करेंगे तो हमें कुछ ना कुछ तो मिल ही जाएगा। और अब हमें यहाँ G का भी पता है। हाँ ऑलमोस्ट सॉल्व लग रहा है। अब ये D की डिग्री काउंट करूँगा तो इसमें DA भी आ ही जाएगा। हाँ तो डबल काउंटिंग, हाँ वही रिक्वायर्ड डबल काउंटिंग हो ही जाएगी।
By the way, is it still streaming?
क्या फर्क पड़ता है? हमें क्या मतलब?
Yeah. Yeah, it is streaming. Also, no host, I don't know. Okay, yeah, maybe make me host instead. Yeah, makes sense.
कौन है होस्ट?
Mayuk is.
RG? मैं आवाज नहीं पहचान पाता।
Yeah, this was me. This was me, RG. Yeah.
आपको क्या लगता है इस प्रॉब्लम पे ऐसे अप्रोच करेंगे तो ठीक ही रहेगा क्या?
I don't know what you're trying. What are you
हम
trying?
तो बस एक JB की डिग्री ऐसे AB स्मॉल AB लिख के डिनोट कर रहे हैं।
Okay.
तो हम ऐसे लिख सकते हैं 2n इज ग्रेटर देन इक्वल टू, ये छोटा है A की डिग्री है AI प्लस AB प्लस AD।
Okay.
इसे लिख के देखें एक बार। मैं कोई भी पेज का कोई भी पेज खोल के उस पर लिख लेता हूँ। So
Also, you can
ये,
directly write on GGP, no? Like that's a
अरे
text
नहीं,
option.
अच्छा टेक्स्ट ऑप्शन है, एक सेकंड में ढूंढता हूँ।
And you can type text as LaTeX.
तो अच्छी चीज़ है इसे। हाँ हाँ, तो कॉल वर्टेक्स, ये याद नहीं रहा, बैड इफ इट हैज टू आउटसाइड थिंग्स गोइंग आउट ऑफ इट। मतलब जैसे H बैड है, आउट ऑफ इट, लाइक H। कहाँ गया?
On the bottom right. A bit
अरे
bottom.
हाँ हाँ दिख गया. हाँ तो ये करते हैं कि कॉल लेट्स कॉल अ वर्टेक्स से बैड जैसे एच बैड है, ठीक है. अब ए और बी तो गुड है, ए कॉमा बी जी, ए कॉमा बी अपना गुड है, गुड जैसे उनका अलग ही टाइप का कॉन्फ़िगरेशन है.
You can
Hi
stop
guys, I'm
sharing.
back.
Okay,
Ritam is here.
Ritam is
I
finally back.
think
You can stop
we
now.
can start now.
Who returned?
You guys doing something?
Ritam. Oh, they were
So I should.
trying a problem from the PSS because you weren't here. They said let's just spend our time productively.
Oh, so should I stop screen? अच्छा.
Okay, so let's start. Vector spaces over. So let's start with the F2 part. F2 is what is called a field with two elements. So it's basically, as a set, you can think of F2 as just being 0 and 1. Now it's not just a set, it's actually a field, but we'll come to the field part later. For the moment, you can think of it as being just the elements 0 and 1. So the point is with 0 and 1, you can label a lot of things. A few examples.
F2 is just 0 and 1.
Yeah, F2 is just 0 and 1, along with some operations. So a vector space, I'll come to the vector space part later. So a vector space over F2. Okay, so when I say vector space, I am only talking about finite dimensional vector space. So finite dimensional vector space over F2 can actually be thought of as a binary string. So say dimension equals n. You can think of this as just a binary string of length n. And that's the basic idea. But the point is, on these strings, we can now do linear algebra. So binary strings are very common objects. You see them pop up all over the place. A very common example would be a set. So say you have the set 1 to n. By the way, a small notation thing. I will be using this to represent the set. The square bracket n thing. So subsets of 1 to n can basically correspond to binary strings of length n, because for each element you can either have the element in the subset or not have it. So if you have the element, you put a 1 there. If you don't have it, you put a 0. So this sort of corresponds to the set 2, 3, so on. 2, 3, but no 4. If there's a 1 and there's a 5. So subsets of 1 to n correspond to binary strings of length n. So now the question is, another example would be the adjacency matrix of a graph. Adjacency.
How was that one-to-one example related to the 0, 1 thing?
Oh, so suppose you have a set 1, 2, 3, 4. Then a subset of this, say 2, 4, corresponds to the binary string 1, 0, 0, 1, 0, 1, because you just put a 0 wherever you don't have an element and put a 1 wherever you have an element. So that's how you get a correspondence between the 2 to the power n binary strings and the 2 to the power n subsets. This is basically the reason why there are 2 to the power n subsets, right?
Basically, each subset maps to some a distinct binary string.
Yeah, every subset would map to a distinct binary sequence of length and vice versa. And the other thing I wanted to talk about was adjacency matrices, which will crop up when you're doing graph theory. Suppose G is a graph. In that case, you define the adjacency matrix of G to be so for the ijth entry, you put a 1 if okay, so let's write in this way. Aij equals 1 if there's an edge vi to vj. So for example, let's just draw some graph. V1, V2, V3, V4. For this, the adjacency matrix would be 0 across the diagonals, because no vertex is connected to itself. 1 and 2 are connected. 1 and 3 are connected. 1 and 4 are connected. 2 is not connected to anything else. And 3 and 4 are connected. So this would be the adjacency matrix of this graph. Is that okay? Like, did you get what adjacency matrix means?
Could you
No,
repeat?
please.
Yes.
Yes.
One second.
So basically, you can think of these 4 rows and columns as corresponding to V1, V2, V3. And the ijth entry has a 1 if Vi and Vj are connected and 0 otherwise. And the diagonal is 0 by convention or definition. I mean, if you have self loops, you might want to put 1s or 2s there. Yeah, so
The transpose of an adjacency matrix is the same, right?
what? I couldn't hear you.
The transpose of an adjacency matrix is same, right?
Yeah, the adjacency matrix is symmetric because I mean, for a simple graph, for like directed graphs, it need not be symmetric, right?
What
But
kind of graphs?
it's guaranteed to be symmetric because I is connected to J if J is connected to I. Now
Also, what if in a graph the vertex A1 and A2 have 2 edges between them?
Those are multigraphs. So for multigraphs, you can just put the number of edges instead of like 1. So if the 2 vertices have 10 edges between them, you put 10 instead of 1. You just put the number of edges between the 2 vertices. This also works for simple graphs because for simple graphs you either have 1 edge or 0 edge, but for more complicated graphs you put the number. So a quick reminder, I was telling you that F2 is a field, right? It's not just the set 0, 1. So the point of being a field is that you can add and multiply over F2. So the addition is, both of these are pretty simple. Like, so addition is given by this table and multiplication is given by this table. As you might, so at F2 can basically be thought of as Z mod 2Z if you want to, like along with the addition and multiplication operation. So F2 can, so that the best way to think of the two elements of F2 is as 0 representing even and 1 representing odd. So 0 plus 0 is 0, 1 plus 1 is like odd plus odd is even plus even is even, and so on. And multiplication you can think of as the same thing. So this basically gives you a hint for the use case of F2. You use F2 when working with parity. Parity. So F2 basically deals with parity. And I should quickly explain what the word field means. So field means a set along with two operations, which in this like addition and multiplication, and they need to satisfy like all the usual properties of addition and multiplication. Like both need to be commutative and associative, and addition needs to be distributive over multiplication. And you need to have additive and multiplicative identities and inverses. So 0 is the additive identity, 1 is the multiplicative identity, and well, 1 is the multiplicative and additive inverse of 1, and 0 is the additive inverse of 0. So there's not much to talk about. I mean, I hope like, yeah, you can think of them as XOR and AND. Yes, you can think of this as being the exclusive OR and this as being the AND, but if you want. Yeah, fields have to be closed under multiplication and addition and satisfy all the usual properties. So I hope this is clear. Like this should not be particularly complicated because there are only two numbers.
So
Now
what
let's
is F2 like? How did you multiply it? Is it a matrix? Like the result was a matrix?
no F2 is the field, right? F2 is that set with two elements along with some operations on those two elements. So F2 is similar to R in some ways.
But when you multiply two strings, the result was a matrix.
No, we are not multiplying strings. We are multiplying 0 or 1 because these are the only elements of F2, right? We haven't moved on to matrices or vector spaces yet. So
Okay.
you can do addition and multiplication over R. You can do addition and multiplication over F2. That's about it. Like you use F2 when you want to talk about parity specifically. Okay. Here after some examples, but I just need to explain what these things are first. So now let's talk about a vector space. So the key ingredients you need for a vector space is the main thing is V, which is what we actually call the vector space. It's just a container of vectors, whatever that means. It is some container of vectors, and you need some field over which it's a vector space. So you need a field such as, in this case, our field would be F2, but usually you work over the field R or C. Like normal people work over R or C. Like F2 is only for doing combinatorics and all that, or computer science stuff. Usually you think of a vector as being, say, a bunch of real numbers. So 1, 2, 3 is a vector over R. 1, 2, 3 in R.
In R cube, right?
It's called a vector space, and this 1 to 3 is an example of a vector over R3. And the ground field in this case is R. And if you think of this as a vector space over R. So vectors are.
Can you please repeat what did you say? If it is a vector over R?
So R is the set of scalars for this vector. So the idea is that for any vector, you can multiply them with an element from R. So you have 2 in R, right? So you can multiply this vector by 2 and you will get the new vector 2, 4, 6. This is called scaling. So the idea is, so this ground field, this is called a ground field. It's also called the set of field of scalars. So scalars provide the numbers which with you can multiply or stretch by. Now, let's look at an interesting case. An example over a vector for a vector space over F2 would be, say, I mean, binary strings of length are a good example of vectors. So this, if this is a vector over R3, this is a vector over F2, 3. And the funny thing is, since F2 only has 2 elements, you can actually only scale by 0 or 1. So scaling by 0 just sends this to the 0 vector. There's a vector called 0, which is basically the 0, as you might or might not have expected. And you can also multiply by 1, which basically does nothing. So the ground field here is F2. And you can stretch vectors by scalars and you can add vectors. So the other thing is you can add vectors. So if you have 2 vectors 1, 2, 4 and 3, 7, 9, you can add them and get a new vector like 4, 9, 13. This is all straightforward stuff. So if you have 0, 1, 0 and you have 1, 1, 0 over S3 over the same vector space, then you can add them. So if you add these two, you get 0, 1. You get 1, 0, 0. 1, 0, 0. Is the addition thing clear?
Yeah.
So
Probably this F2 cube is nothing special. I think you can replace 2 by any prime.
yes, you can replace 2 by any prime, but since it turns out that 2 is kind of useful since 2 is pretty small, and so the thing is, for a lot of these Olympiad problems, you will be working with parity, and when you are working with parity, you want to work over F2. Yeah, you can work over other fields like F3 or I don't know, F19. These are all perfectly valid examples of fields you can work over. But we will mostly be working over F2 for practical reasons. So I told you what vector spaces are, but what do you do with them? So the question is, what do you do with these vector spaces? So you have these vector spaces, but why did you define them this way? So why do we have these scalars and vector addition? So the idea is, the main idea of vector spaces is taking linear combination. So given V1, V2, given some vectors in V, a sum of this form CIVI is called a linear combination. And C1, C2.
So V is the vector space over F2 or any general vector space?
Or any field F. Or actually, let me do some renaming. Let me call the field K, which is usually what is I'll call the field K and I'll replace this K as a subscript with M because that's more traditional.
What is V and K?
V is the vector space, K is the field over which it's a vector space. So V could be like R3 and K could be R, or V could be like C7 and K could be C, or V could be like B4 and K could be F, F24 and K could be F2. Like V is just a vector space and K is the field over which V is the vector space. Was that clear? Like?
CI is one dimensional, right? Actually.
I mean, you can think of them as one-dimensional vectors, but we actually call them scalars, and it's better to think of them as scalars. So you should think of them as things you multiply vectors by. Things you multiply vectors by. That's the best way to think of them. And these things, some CIVIs are called linear combination. This is called a linear combination of V1 to Vi. It's called a linear combination. Is the definition of this linear combination thing clear?
Yes. It also generates like a plane in R2, like if you consider two-dimensional vectors, right?
So yeah, if you are given, so that's technically the span of those two vectors, not the linear. So these linear combinations generate what is called the span of these vectors. So the set of all linear combinations, or like over all possible scalars, is called the span of V1 to Vm is the set of all where so the span is simply the set of all possible linear combinations. It turns out you can think of the span as being the smallest subspace of V being generated by these vectors. So a subspace of a vector space is, well, what you think it is. So it's another vector space over the same field with the same scaling and addition. It's also a subset of V, and the key point is it's closed under addition and scaling.
Why is it closed under this set is closed under multiplication?
This is closed under multiplication because if you multiply, let me write it somewhere else. So see, if you multiply this sigma CIVI with a constant C, then it's C times sigma CIVI is simply sigma CCI times VI, right?
No, but if we multiply the two elements of the set, then they might not be in the same. Like
You can't multiply two vectors. These are vectors, right? You can't multiply vectors. You can only multiply vectors by scalars.
Okay.
It does not make sense to like multiply vectors, or I mean, you can make sense of that, but we won't be talking about that yet. So I'm only talking about scalar multiplication. So to be a subspace, the whatever set of vectors you have needs to be closed under scalar multiplication as well as addition. So if you add two vectors of this form, you get another vector of this form, which should be pretty obvious because, well, if you have some sigma Ci Vi and some sigma Vi and some sigma Di Vi, the sum is simply sigma Ci plus Di times Vi, right? So it's another vector in the set. So it turns out that these vectors generate a subspace.
Can you define the span once again?
Okay, so span of V1 to Vm is the set of sigma Ci Vi, where C1, C2, Cm are arbitrary scalars. Is that clear? So let me give an example. So suppose you have the vector space F24, right? And you are given, say, a couple of vectors 1, 0, 1, 1, and 0, 1, 1, 0. Say you are given these two vectors. What's the span of these two vectors?
C1 the first vector plus C2 the second vector.
Yeah, but
C1
the span is a set, right? So what are all the elements of the set? Can you tell them one by one?
There are two
CI.
only.
CI.
What?
Elements of the form CI.
Yeah, I told you what the forms are. I want
there
to
are two
give you the
only.
specific elements, right? F24 only has 16 elements. Out of these, the span of these two has only 4 elements. I want you to tell me all the 4 elements.
1 0 1 1 0 1 1 0 0 0.
Yes, this is correct. These are indeed the 4 elements. So do you see why? So if you can choose like C1 times 1 0 1 1 plus C2 times 0 1 1 0, and C1 and C2 can both be the 0 and 1. So if you select both 0, you get the 0 vector, which is 0 0 0 0. If you select 0 and 1, you get the, if you select 1 and 0, you get the first vector. If you select 0 and 1, you get the second vector. And if you select 1 and 1, you get the vector 1 1 0 1. So these are all 4 vectors that you see in this vector space. Is that clear? Like, did you understand what the span is?
Yes.
I'll give one more example. So if you have 2 vectors over, so say you have 2 vectors 1 2 and 3 4. So actually I'll give it 1 2 0 and 3 4 0. Suppose these are 2 vectors over R3, where R is the ground field. So what's the span of these 2 vectors?
That is C1 and C2 thing only.
CI plus 3 CJ, comma 2 CI plus 4 CJ, comma 0. CI CJ can be anything, and these vectors.
Yeah, so there's a simpler way to write that, right? So the span is a set, remember? So I want you to give me a description of the set in the simplest terms possible.
C1 times 1 comma 2 comma 0 plus C2 times 3 comma 4 comma 0.
I mean,
is it the real numbers?
there's a simpler way to say that.
R2, R2.
Like R square.
It's an embedding of R2 onto R3. So imagine 3 space and imagine the XY plane. This basically describes the XY plane in 3 space, like the span of these 2 sets. So if you scale C1 and C2 appropriately, you can get any vector in 2 space. So
like if it is R2, shouldn't the vectors be independent?
yeah, these 2 vectors are independent, right? So let me show you how to get the vector. So if you scale this by 2 or if you scale this by 1 and this by -2, you get the vector 1 0 0, right? So 1 0 0 is in the set, and once you have 1 0 0, you can easily get. So after that, you can just take half of 1 0 0 and subtract. You have 1 0 0 because you can take 1 times this 3 4 and minus 2 times 1 2 0. So that's 3 4 minus 2 4, right? Which is
the
1
base is
0.
all R, right?
What?
The base is all R, right?
The ground field, yeah, the ground field is R.
I don't think so. The rightmost thing will always be 0.
Yeah, so the span that you get is essentially xy0 for xy in R. This is the simplest description of the span. It's a two-dimensional subspace of R3.
So in general, is there any fast way to derive the span of any given vectors?
I mean, you can just imagine what it would be. Like you see these two vectors and these are linearly independent. So, oh, by the way, I need to define linear dependence and independence actually. So I'll actually talk. Yeah. So let me talk about linear independence. So the idea of linear dependence or independence is that, so suppose you have m vectors v1, v2, vm as before, and suppose you have suppose there exists c1, c2, cm in K such that sigma ci vi equals 0, and these are not all 0. Then we say that v1, v2, vm are linearly dependent. And if they are not linearly dependent, we call them linearly independent. So basically, you should have a non-trivial linear comp. By non-trivial, I mean not all Ci should be 0. So if you put all Ci 0, then you will obviously get 0. But if you have any non-zero linear combination of the Vi, which adds up to 0, then you say that the Vi are linearly dependent. Basically, there's a linear combination. Okay, let me give an example. Consider these three vectors in F3, F23, 1 0 1 and 0 1 1. I claim that these three are linearly dependent because if you add these three vectors, you actually get 0. Can you see that? So there's another way to face linear dependence over vector fields, vector spaces. This is kind of why you want the thing you are working on to be a field and not a ring. You actually need division to restate. So you can say this as Vm equals sigma. So you can rewrite this equation as Vm equals sigma Ci by Cm Vi. Yeah, so another way of saying like things are linearly, assuming if Cm is not 0. So basically what linear dependence means is that one of these m vectors can be written as a linear combination of other vectors. So it's not as general as things could be. So in this case, this third vector can be written as a sum of the first two vectors. So these are not linearly independent. Is there any confusion?
Which are not linearly independent in this example, F32.
What? I can't
Which
hear.
which thing is a linear independent in this example of F32?
What do you mean is linearly independent? I don't get you. Could someone else repeat what he just said? What is linear independent in? Oh no, these are not linearly independent. These are linearly dependent. That's what I'm saying. That these three vectors have a linear dependence: 1, 1, 0, 1, 0, 1, and 0, 1, 1. So the third vector 0, 1, 1 can be thought of as the sum of the first two vectors, or some other way. Or in the other definition, you can think of these three as having a non-trivial linear combination, which is the sum as adding up to 0. Yeah, these three vectors. Yeah, they are dependent. That's what I'm trying to explain. Yes. So in the previous example, we were talking about 1, 2, 0 and 3, 4, 0, right? So these two vectors are linearly independent. I mean, for two vectors, linear independence is a straightforward idea. So there are multiples of each other, there's a linear dependence, otherwise there's no linear dependence. Is the idea of linear independence clear, or do you want more examples of
Clear.
In the last you said that they are the multiples. That is true in R only, no?
No, that multiples is true over any field.
Oh.
So it's true over F or C or
So
whatever.
what is the multi, like, can you tell that in that this example 1, 1, 0, 1, 0, 1, 0, 1?
I mean, multiplication over F2 is trivial because you can only multiply by 1. And multiplication by 1 is not interesting. Multiply by either 1 or 0. And neither of them are particularly interesting examples of multiplication, right? If you multiply by 0, you get 0. If you multiply by 1, you get what you started with. So 1, 2, 3, and 7, 11, 19 are linear independent. But why would they be linearly dependent? No, though these two are independent. I mean, I don't. Yeah, no. So 1, 2, 3, and 7, 14, 21 would be dependent. Because 7, 14, 21 would be a multiple of 1, 2. Oh, like, I mean, the definitions are written on the board. So this thing here can be thought of as a definition. If there exists C1, C2, Cm, not all 0, such that sigma Ci, Vi is 0. And if say Cm is, or yeah, if Cm is non-zero, then you can think of Vm as being a linear combination of the other VMs. So if some vector is a linear combination of some, since one of them is non-zero, there's some vector here which is a linear combination of all the other vectors, right? So that's what we mean by linear dependence. It can be written as a linear combination of other vectors. If no one else has any other doubts, I'll clear this code as well. And I'll define what is called a basis. So the basis is a set of vectors that do both of the following. Span the entire vector space and are linearly independent. So, do you understand what I mean by span the entire space?
So their span is the entire space, right?
Yeah, that's exactly what I mean. So, a very simple example of a basis over, say, so the most trivial example of a basis is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Can you see why this is a basis? Or
Yes,
this is a basis
yes.
over both R3 and F23, by the way. This, I mean, it should be pretty obvious why this is a basis, but for example, you can create other bases. So over R3, for example, 1, 0, 0, 1, 1, 0, and 1, 1, 1 is also a perfectly valid example of basis.
Oh, by the way,
Or this is also a valid example of a basis over F23.
how do you obtain 0, 1, 0?
What? How do I obtain?
0, 1, 0 in F23.
0, 1, 0?
Yes.
So you just subtract the first vector from the second vector, right?
Subtraction defined.
I mean, subtraction. So for any vector, you can multiply by -1, right? Because -1 is an element of R.
But you said that
And
in the F2, 0 and 1 are only there. How is the minus?
no, I'm
1?
talking about R in this case. So in R, you can multiply by 1. Even in F2, you can actually, so in F2, you actually have -1 equals 1. So the definition of -1 is that number for which -1 plus 1 equals 0. So in F2, you already have 1 plus 1 equals 0, right? So basically, you can think of -1 and 1 being the same thing. So even in F2, you can talk about subtraction. So in F2, subtraction is just addition, which is the funny thing. That's unique to F2 and or vector spaces of characteristic. So is the idea of this basis thing clear? So the basis is a set of vectors which are linearly independent and generate the whole space. So the main result I want to talk about is that every basis has the same size. And in fact, this size, this is defined to be the dimension. So the size, every basis has the same size, and we call this same size which every basis has as the dimension. So the dimension of a vector space is simply the size of some basis. This size is called the dimension. So for example, 1, 0, 0, 0, 1, 0, and 0, 0, 1 is one basis of F23 or R3. So the dimension of F23 or R3 is 3. And similar, another possible basis was this 1, 0, 0, 1, 1, 0, and 1, 1, 1. And the size of this set is also 3. So the dimension has to be. So this is a theorem, and I'm not going. You can. This is a very standard theorem in linear algebra. You can look up the proof if you want, or you can.
Well, if we assume that n is the dimension of the vector space, and if we choose any n elements which are linearly independent, then will it be true that property 1 is also true?
Yes, that's actually another theorem. So if you have any two of this, where one is just span space, 2 is linearly independent, and 3 is has size n. If you choose any set of vectors which satisfies two of these three, then it will satisfy the third. So if you choose any n vectors which span the entire space and are size n, and then they are guaranteed to be linearly independent. Or if you choose n vectors which are linearly independent, then they are guaranteed to span the entire set. Or if you choose n vectors which span the entire space and are linearly independent, then they are guaranteed to have size n. You can sort of intuitively feel why this is true. And this is also a very standard theorem. You can look up the proof. I won't actually be doing the proof now because I want to do some problems.
Any good source where I can find the proof of these?
I mean, you can read Napkin if you want. Napkin is pretty decent. Or you can pick up any random linear algebra textbook. Any linear algebra textbook is guaranteed to have a proof for these two results.
Okay.
So let's see some examples of the ideas that we have covered. So let me give you a problem. This problem is called one mania. I think it came in TST 2018/2. So the problem is there's a directed graph. Each vertex, I hope everyone knows what a directed graph is. So a directed graph is just a graph where the edges are directed. So the edges are basically like arrows. So they start at some point and end at some point. So they are oriented at this. Each vertex has two incoming and two outgoing edges. Exactly two incoming and exactly two outgoing edges. So by an incoming edge, so this edge would be considered an incoming edge for V2 and an outgoing edge for V1. So for every vertex, you have two edges coming into it and two edges going out of it. Prove that the number of ways to delete half of the edges such that each vertex only has one incoming and one outgoing edge left. Is a power of 2. Is the statement clear?
What does that is a power of 2 mean?
I mean, do you not know what a power of 2 is? Like what?
What does it
Oh,
mean?
so the number of ways is the power.
Okay. No, got it. So I think we can define the adjacency matrix in this directed graph, and then like in each row there should be only one element, and in each column there should be only one element. Something like that we can do.
I'll let you guys think about this problem for like 5 minutes.
can it have a directed edge to itself?
No, all the directed edges must be between different vertices, I think.
Okay.
Can two vertices have directed edges in both directions?
Not necessarily. Oh, they can have, yeah.
They can, right? Yeah.
They can. Oh no, they can't. It's not allowed. It's given in the problem. So actually, let me just copy paste the original problem statement. I will say let me just. Let me clear everything on. If we assume n vertices, then this is saying that then the problem is equivalent to say the directed cycles of length. No, the entire graph need not be one single directed cycle. It's going to be a union of directed cycles, right? After deleting the edges, or even before deleting the edges, the vertices need not be connected.
I think there must be some invariant.
Yeah, no, so let me give you a hint. Yeah, just do it for connected. So here's the thing, you might be disconnecting components when you cut off some edges. So this is not an obvious thing. Like this is a very awkward way of going about the business, I'd say. So I'll give you a small hint. So vector spaces over F2 always have size 2 to the power n. Like the size of the vector space F2n is 2 to the power n. So I'll give you a bigger hint. So you have to show that the set of solutions to this
I think I just
problem
did it.
can be made into a vector space over F2, and then the conclusion will immediately follow because.
Is there a way that
I think we can do it
Can
like
we
that.
make it
Like if we consider a agency matrix, and if we consider like the rows to be the cities, and the rows to be cities also. Yeah, so like if we divide the city set into two, and we split it into rows and columns, and uh, and we mark zero if they have a common path between them, and if they don't have, then we mark one. Then I think this should be a nice idea.
Can you write it out? I understood nothing.
Is there a way that we can use like vectors over F to get a matrix, something like that?
Why do you want a matrix? Like you just want a
Like
vector space, right?
if we define the adjacency matrix of this graph,
Adjacency matrix won't work, right?
like if we define the
You need. So what you are going to get is a vector space over. So think of the vector space over all the edges. So number the edges, say 1 to m, and think of the m-dimensional vector space over all the edges. The vector space we want is going to be a subspace of this vector space, because we are essentially the conditions we have. The condition we have is that the number of roads entering and on the number of roads entering and leaving each vertex, right? So the condition is that we have is a condition on edges. So for two edges, if the two edges are incident on the same vertex, then the two edges must add up to 0. That's or add up to 1 actually, like the things that we do with the two edges.
Will this require flows?
No.
Actually, I didn't get the hint you gave, like number the edges.
So think about it. So basically we are deleting edges, right? So our deletion of edges can be represented by a vector. That's fine. Yeah, so a deletion of edges can be represented by a vector. So suppose the edges we have are E1, E2, EM, right? So if you are deleting the edge EI, you put a 1. So if you are deciding to delete E1, put a 1 here. And if you decide to keep E2, you put a 0 here, and so on. So you form a vector like this, right? So the idea is some subset of these vectors are valid in the sense that they satisfy the condition that we want.
Okay, so
The
yeah, so can
idea
you
is
hear me
that the
properly now?
condition that we want can be written in terms of like linear algebra. And once we have that, we can prove that the subset of like valid deletions or valid vectors that we have is actually a subspace of this entire vector space. So being a subspace, it's also a vector space over F2, right? So being a vector space over F2, it must have like a size 2 to the power n, which would conclude the proof. Oh, by the way, you also need to show that this has at least 2 elements, because the empty set and the set with only one element. So the empty set and the set with only 0 are also kind of vector spaces over F2. So you need to show that it has dimension in at least 1. You need n is
Hello?
greater than equal to 1. So you need
Can you
to
hear me
prove
now?
that as well. And so that you can prove even without linear algebra. Like that's pretty straightforward. You just need to show that there's some way to delete the edges. What are these C1 cities?
These are cities.
Oh, okay.
Yeah, so like yeah, so like I think that like if we divide the set of cities into two and we split it across rows and columns and make such tables.
What do
Like
you
this.
mean by divide the set of cities into two?
Like put half cities here and half here. No, wait. No, no. No,
How is
actually it
that
won't
going
work.
to do anything? Like,
Because there isn't a bipartite graph. This
yeah,
one.
there's exactly. So I don't think this is going to work. Do you guys want more time to think, or should I tell you the solution, full solution?
Just 2 minutes.
Yeah, okay. So I'll be back in a couple of minutes.
Can you give us more hints?
I mean, I gave you the biggest hint, right? So you create a vector space over the edges.
I think what we can do is that if suppose there E1 is edge connecting x to y with x go like a road from x to y, then we can assign the number x minus y to E1, and like we want that the sum of all the edges equal to 0.
No. What? That's a you are losing most of the conditions if you are doing that. We are not assigning numbers to the vertices. We don't care about the vertices. We are only
No, I am assigning to edges.
okay. So if you're so what's the subspace that you are getting?
Uh,
What exactly are you trying to what
I also
exactly are you
don't
trying
know.
to achieve?
This just seemed a nicer representation.
What's your representation? I did not get your representation.
Like suppose there is a edge, suppose E1 connects two cities x and y with the edge directed towards y, then we assign the number x minus y to E, and we want to delete like we want to delete suppose the then we want to delete the sum of these edges such that not all but some such that sum of the deleted edges is 0, like the number assigned.
Yeah, so you only get one condition. You have one condition for every single vertex. So you are losing almost all of the conditions. So this is not going to work. You have to preserve every single condition because you are counting numbers, right? So I told you to look at this as a vector over F2M, right? So the conditions you have, okay, let me just tell you the solution. So the condition you have is that every city has exactly one node leaving it and one node entering it, right? So originally, suppose you had a city, let's just call it C, okay. So suppose you had EI and EJ both leaving the city. Or rather, EI and EJ are the entries in the vectors corresponding. Okay, so I'm going to label the entry, I call this X. And I'm going to label
Does this
the
problem
entry
also have a
what?
does this problem also have a simple graph theory solution?
Yeah, this definitely has a purely graph theoretic solution. Like actually the first solution which I figured for this problem was purely graph theoretic. But I don't want
Can
to
you
talk
motivate
about
that
like
also?
pure graph theory now. What?
Can you motivate that also a bit?
I mean, it's essentially the same solution, but in graph theoretic terms. So that solution will essentially use okay, that's actually a cleaner solution, a cleaner version of this solution, but it requires more thought. So actually, let me do this solution first, because the graph theory solution is essentially a prettier version of this solution, in the sense that it basically tells you what the vector space is precisely, instead of just telling you there's some subspace which works. Like it can be thought of in that way, but
What do you mean by subspace?
I mean, I defined subspace earlier, right? So a subspace is just another set of vectors which a subspace is a subset of vectors from this. So it's a subset of F2M such that which is closed under the addition and scaling. So scaling is non-existent, which is closed under addition.
Okay.
Subspaces are themselves vector spaces over F2. Okay, I should have probably have explained what a subspace is better. So maybe I'll give an example. So what do you mean by final answer? This is a problem where you have to prove something. There's no answer. Oh, you mean the proof I was going there? Yeah, sure. So basically, we want exactly one of these two, EI and EJ, right? And so this condition translates to XEI plus XEJ equals 1 in F2. So we want to keep one of these and delete one of these. We don't want to delete both of these or keep both of these. Keeping both of these would correspond to taking 0, 0, and deleting both would correspond to 1, 1. And neither of those add to 1. Only 1 and 0 add up to 1, right? So we basically want the entries corresponding to these to add up to 1. And this is a linear equation. Oh, by the way, I should have actually discussed this before. Yeah, so similarly for every vertex with every vertex and pair of incoming edges, we can also define, like, suppose this is just these are I mean, let me just reuse symbols. Okay, so this I and j are some other arbitrary numbers. So if you have two incoming ei and ej, you just put the same equation there. So basically, you have a large number of equations over this entire space. So here's the key point. if you have a vector space and if you have a bunch of equations over the vector space, bunch of linear equations over that vector space, then you are guaranteed that the set of solutions to that linear equation. So yeah, you are guaranteed that the set of solutions X to this set of linear equations that you have. So you have something like you have two linear equations for, you have something like 2n linear equations, right? So the idea is that the set of solutions to a system of linear equations is guaranteed to be a subspace. Why is
What
that?
do you mean by subspace?
I think that's by this definition.
That's not so. I guess I
How do
should
you
have.
define a subspace exactly?
Yes.
So suppose you have a vector space V, and then V, which is a, suppose W is a subset of V, then we call W a subspace if given any W1, W2, and W, we have that, and C1, C2 in K, we have that C1, W1 plus C2, W2 is in W. So basically, W is a set of vectors which is closed under linear combinations.
Okay.
W is a vector space essentially,
Where
and it's also a subset of V.
Oh, where is the V here? Like
Where?
I'll define
Like
W1
if we
and
consider a subset of them, won't dimension will be decreased?
Yeah, dimension will decrease. So W is guaranteed to have. So you are guaranteed that if W is less than or equal to dimension of V, and it's
Where
equal
is
only
V?
if they are the same space. So it's actually going to be strictly less than unless they are the exact same space, in which case equality holds.
Okay.
So you get my point. So W is a vector space by itself, like if you forget about V, and W is as a set, W is a subset of V. So in that case, we call W a subspace of. Let me give an example. Consider F24, right? Oh, again, remember those span things? Those spans are examples of subspaces. Again, if you remember F24 and the example I gave you, like 1010 and whatever, 0110. These four vectors form a subspace. 0, 0, 0, 0. Every subspace must have 0, right? Because, well, you might choose C1, C2 to be 0, in which case you will have to have 0. And the sum is 110. These four vectors are a subspace of F24. This is an example of a two-dimensional subspace of F24. Is the definition of a subspace clear?
Yeah, clear. But I don't think the solution set would be a subspace because, for example, 0 plus 1 is 1, 1 plus 0 is 1, but if we add the 2, we get the 2, which is not equal to 1.
No, but 1 plus 1 is 0, right? Sorry, why? Yeah.
So we don't want 0, we want 1 now.
Where, like,
Like,
what are you talking about?
Like we want 1 here. So if we add 2 such solutions, we will
One
get
where,
2.
like, don't just say here. I don't understand what you mean by here.
I've marked like it in red.
You want what?
We want this linear equation to satisfy, but if we consider 2 solutions of this and add the 2 solutions, there will not be a new solution.
Not. Oh, right. You are correct, I think. So
I mean,
actually,
he's just saying that 0 plus 1
yeah. You are right. So I should have been a bit more specific. You are correct. This is not a subspace. This is actually a translation of a sub. So the subspace we want corresponds to the homogeneous version of all these equations. So when you have a system of linear equations, you have what is called its null space. So consider any solution. Consider any solution to like uei plus uej equals 0 for eij, where eij are like two edges incident on the same vertex, like this or this. So consider the set of all this. This is a set of linear equations, and these the solutions to these equations form a subspace. Yeah, you are correct. Yeah, these don't form a subspace. These are the ones that form a subspace. So, is it clear that solutions to these to this set of equations forms a subspace?
Yeah.
The solution are 1, 1 and 0, 0, right? So
No,
that
that's just for one equation. So you have one equation. Let me actually give you an example. Let's just draw a graph. Okay, so
is it a theorem that every subspace can be like represented with a basis?
yes, every subspace for finite dimensions is kind of obvious. In fact, every spanning set, every linearly independent set can be increased to a basis. So you can essentially just keep taking random elements that are linearly independent from what you already have, and you will get a basis. So suppose you have a vector space W, right? You can just choose a W1 in W, and then choose W2, which is linearly independent from W1. Then choose W3, which is linearly independent from W1, W2. Then choose W4, which is linearly independent from all of the previous one. When you are no longer able to take a linearly independent vector anymore from like all the previous vectors, at that point you already have a basis.
Oh, yeah.
Because since you do not have any other linearly independent elements left, that means that every vector that's possible is already generated by linear combinations of the vectors you already have, which means that any set of vectors you have is guaranteed to be linearly independent by construction. So it follows that it's a basis.
Okay.
So this is how you create a basis. Creating a basis is pretty easy.
So we just need to prove this, because once this is true, then it is clear that basis has length 2 to the power n.
You still need to prove one other thing, that this set of equations has a solution, or this set of equations has this set is guaranteed to have a solution because all zeros is the solution and all ones is also a solution and whatnot. So all you need to prove is that this set has a solution. So, so the idea is that once you have a specific solution x to this set of equations, then adding any other solution u, then x plus u is a solution. Like if x is a solution and u is a solution, then x plus u is also a solution, because x plus u ei plus x plus u ej is simply xci plus xej plus uei plus uej, which is 1. So basically, once you have a specific solution, every other solution is guaranteed to be that particular solution plus a solution of this. So the converse also applies. If you have a solution x and if you have any other solution y, then x plus y is a solution of this set of equations. So
I think you meant x
so
minus y.
you can write y equals x plus u for some for all solutions. So you just need one specific solution, and you get 2 to the power k solutions corresponding to each possible solution to this equation.
But then we need to do another thing. Question is asking to prove that the power is greater than equal to 2. So that doesn't prove by this.
Yeah, exactly. So what we need to do is that we need to, also by the way, is everyone else following the discussion? Just ask me if you have any doubts.
Also, why did we consider
Can
the
you
2n
motivate and
equations?
summarize the
why did we
motivate and
consider what?
supervise the solution till now.
I was asking like n of the equations would imply the other n because of the first condition. So why did we consider two n equations instead of n?
What do you mean by an
Like
equation?
you took care of both things, that the incoming things and outgoing things. But if we just take care of the incoming things or the outgoing things, the other thing will be automatically done, right?
No, it won't. Because see, you can have a vertex C1 with two incoming edges, but only one outgoing edge, right?
But that is not
How-
possible because of the first thing.
Why is that not possible? Like, if you only deal with outgoing edges, you are not going to guarantee that incoming edges behave correctly.
No, if we only guarantee if we only guarantee this thing, then aren't we just fine? The other incoming thing would be done automatically.
Oh no, so these EI and EJ are different from these EI and EJ, right? So this is a different equation from this one because we have different. I should not have used the same notation. So if I think of this as EI0, EI, EJ0, EI1, EJ1. These are two different equations. So you have two and different conditions that you need to satisfy. So two and different equations.
Oh yeah, I messed up, I guess.
Can I share my solution? Like it's not fully done, but almost done.
Let me finish. You can put that on Discord, I guess. Like if you have a graph theoretical solution or something.
No, no, not the
You
graph
can,
theory one. The adjacency matrix one. It seems a bit easier.
yeah, you can put it on Discord.
Sure.
Uh,
Right now, after class.
I'll check it after class.
Sure.
Okay, so was everything else clear? Like why solutions to this correspond to solutions to the original problem that we have, and why solutions to this set of equations correspond to set of solutions to this set of equations.
Yes.
So we basically need to count solutions. We need to find one solution to this. Okay, so one thing is that the u being the all ones vector is a solution to this equation. That should be obvious, right? Because if it's all ones, then it's obviously a solution.
Yeah.
So u has dimension. So the subset u, which is the space of solutions of u, has dimension at least one. And at this point, we only need a specific solution to this. That would guarantee that the dimension is at least. So the dimension at least one guarantees this part. And we still need to guarantee that some solution exists. That's the only thing left.
Yeah.
So that part you have to do graph theoretically. Like,
Yeah, I think we can move like a path. We can first go from one
we can
vertex to
essentially
other.
start somewhere and just keep choosing one of the two. It's guaranteed to work. Like it's pretty straightforward. You just select a city, and out of the two outgoing edges, you just choose one of them randomly. And this is guaranteed to work. At some point, you are going to so what's going to happen? So what are the problems you can run into?
But one problem is that suppose there are n vertices and we have a n-1 cycle, then the nth vertex would not be covered.
Wait a second. You can't have an
Or maybe that is not a problem. We could give a counting argument maybe.
no. There's a more straightforward way. Let me just Or we could actually do a linear algebra argument. So there can be zero solutions to this set of equations only if some linear combination of these equations gives us 0 equals 1, right? Like there's an inconsistency.
Yeah.
So suppose there is such a linear combination that gives us 0 equals 1. So you have to add up an odd number of equations. Wait a second.
I think the graph theory thing is simple enough.
Yeah, I think that works too. So let me think for a minute. Oh, right. No. So for the graph theoretic argument, what you have to do is when you take an edge like this from, say, C1 to C2, there's another incoming edge to C2, which you're not only deleting the other outgoing edge, you're deleting the other incoming edge to C2, right? So you have to take the other outgoing edge from C3. So it's essentially alternating between. So if you're taking an outgoing edge from C1 to C2, you have to delete the edge from C3 to C2, which is the other incoming edge to C2, which means you have to take the outgoing edge from C3 to wherever it goes, C4. And
I think that will automatically happen.
Yeah, that's going to automatically happen. I'm just saying what you're going to do. So this is a different way of like doing the path thing. But instead of you choose an outgoing edge, you guarantee that some edge is not outgoing, you choose the next outgoing edge. It's not as a single path, but in a different way. You guarantee that this is not an edge, and just keep doing that until you get back to where you started, and then you can just select some other city and keep doing that all over again. And this is also the original argument that I thought of. This was probably the intended solution. So this also guarantees that the solutions are a part of Q. So this is a more straightforward way of arguing that the solutions are a part of Q.
What is the argument?
So for create a new graph whose vertices are the edges of the graph that you are given, of the road graph. Okay, and we connect two edges if they are both incoming edges to the same vertex or both outgoing edges from the same vertex. Okay, in that case you connect those two, and it turns out that every single edge so in this new graph, every vertex must have a degree 2, one corresponding to the other edge with which it's, suppose you have this edge E from V1 to V2. So E is connected to this other edge E2, which is the other edge of V2, and it is connected to E1, which is the other edge of V1, and it's connected to nothing else because there are no other like these two vertices have no other edges in common, right? So this gives you a graph where each vertex has degree 2. So this graph is essentially a union of cycles. And now the argument is that for each cycle, and the other part is that you need to prove that each cycle is of even length, which is pretty straightforward graph theoretically. And after that, you basically have to choose edges alternatively on each cycle for the solution to work, because you can't choose adjacent edges, and you can't have two adjacent edges which are neither of which are chosen, because the edges here correspond to vertices here, right?
What does it mean by choosing an edge in the new graph?
I mean, choosing an edge in the new graph is the same as choosing an edge in the old graph.
But
Like, by edge, I mean a vertex of the new graph. The vertices of the new graph correspond to edges of the old graph.
okay.
Right? So you just choose you must choose like edges alternatively. So you can choose E here, then you can choose E1 or E2. So you have to choose the one after that. And you can't, since each edge in the new graph corresponds to a vertex in the old graph, you can't just leave both of the edges next to it untaken, because the vertex is not going to be happy about it. It wants to have at least one outgoing and at least one incoming edge. So the only way to satisfy it is to choose vertices alternatively. You can prove that each of these cycles are even, and after that you can choose edges alternatively in two ways, either as like E2, E1 and so on, or E and this vertex and so on. And the same for every single cycle. So the number of solution is simply 2 to the power number of cycles.
I think length of cycles also matters.
No, length does not matter. So you only have two choices, right? No matter what the length. If you have this, you can either choose these two or you can choose these two. If you have like a hexagon, you can either choose these three or choose these three. There are only two choices for each cycle, so it's simply 2 to the power number of cycles.
And can you once repeat the existence of a solution argument?
Existence
like
of
this is a
solutions.
bit ingenious.
So the existence of solutions is simply stating that each cycle is even.
Is there a simple way, because this is kind of ingenious, this construction?
Yeah, so the simple way was the linear algebra thing. Like, it's just shut off your brain and just do everything. Like, just write out all the equations and you know that the solution space is going to be a vector space. Like, those are all standard results. So you just switch off your brain and apply linear algebra and you're done.
No, but we didn't prove, we were unable to prove the existence of a solution using linear algebra, right?
No, you can do that using linear algebra as well. I told you, right? You need to have an inconsistency in this set of equations. So to have an inconsistency, you need some sum of these equations to add up to 0. Give us 0 equals 1. So to have 1 on the right hand side, you need to add up an odd number of equations. For an odd number of equations, what you get is that so each equation is either incoming or outgoing, right? And each of these EIs occurs exactly in one incoming and in one outgoing equation. So when you add an odd number of equations, you either have more incoming equations or more outgoing equations. But in that case, there must be some EI which does not appear in both an incoming and an outgoing equation, which means it can't be 0. So it means that the right hand side is not a linear independence, which is a contradiction.
Why, if we have some equation like x1 plus x2 equal just a second, x1 plus x2 equal x2 plus x3 equal x3 plus x1 equal to 0, this is inconsistent, right?
Yeah, exactly. So this is the problem, right? So each of these equations is either an incoming equation or an outgoing. So you need to label this as either incoming or outgoing.
Yeah.
But here's the problem. You can't have x1 in two incoming equations or two outgoing equations.
It is in one only. It is in one incoming and one outgoing.
Where, so if x1 plus x2 is incoming, you need x2 plus x3 to be outgoing because x2 is common, right? And if x2 plus x3 is outgoing, then you need x3 plus x1 to be incoming. But then x1 is in two incoming equations, which is
Oh,
false.
yeah, got it.
This is essentially the same argument as the odd cycles, but the difference is that in this argument, you just do the most natural thing and this is automatic. While here you need to actually figure out the entire thing. So basically the idea of using linear algebra is that you use all this higher math technology that's already available and do the most natural thing and the solution follows automatically. While in these solutions, these kinds of solutions, you have to apply your brain, which is more difficult. I guess I wanted to do another problem, but I guess I'll do it the next day. Or actually, this one won't take that much time. Let me just do it quickly. They're all drawings. So this problem is called odd town, or as some people call it, it's the odd even town. There's a town with n people, and you want to form, and these people want to form m clubs. So, but the clubs have some rules. So these are two rules all clubs must satisfy. Each club may only have an odd number of members.
They are from M clubs or N clubs?
N people, M clubs. There must be an odd number of members in each club. And any two clubs must have an even number of members in common. So what is the maximum possible value of n? Or actually just prove that m is less than or equal to n.
These were
If
maximum values N mean.
And prove that m is less than or equal to n. Yeah, n is the maximum possible value of m. I mean, yeah, proving that n clubs is possible is pretty simple. Just create one club with one person in it. Like just create a club with the first person and create a club with just the second person and so on. So each
So
club
can
will
there
only have one
be
person. What?
Can there be a person which is in no club?
Yes, and there can't be a club with no members, but only because 0 is not odd, and we require each club to have an odd number of members. But there's no restriction on the number of clubs a person can be. A person can be in 0 clubs, a person can be in all clubs. Everything is fine. These are the only two restrictions that we have. Each club must have an odd number of members, and every pair of clubs must have an even number of members in common. I'll give you 2 minutes to think, and I'll discuss the solution after that.
We have to prove M less than equal to N is possible and M greater than equal to N plus 1 is not possible. This is what we have to prove, right?
Yeah.
Yeah, so the lecture is about to end, like once I finish the solution. Anyone has any leads or any ideas?
Most really we will have to write in that F2 form, and basically the condition that any two clubs have an even number of members is saying that whenever we add two vectors, then the number of zeros there would be even.
I think we'll get a n-dimensional vector space and an m-dimensional subspace of it maybe.
So, okay. We don't want to add the vectors. We actually want to take the dot product. So,
What I was saying was that we could take a n-dimensional vector space and get an m-dimensional subspace of it maybe.
yeah, that is correct. But how does that conclude? So how do you conclude that linear independences are bad? Linear dependences are bad. So if m is greater than n, you will get a linear dependence. But once you have linear dependence, what's the problem with that? That's my question.
How do we
So,
get the linear dependence?
okay, so suppose for each club CI, we define the vector CI to be like 0, 1, and so on, with zeros if person 0 if person PI is not in the club, and 1 if person PI is in the club. So this does not contain P1 but contains P2, something like this. So we get M clubs like this, M vectors, and I want to define the dot product of two vectors here. So you define Ci dot Cj to be, so if suppose these entries are AI1 and so on, and or CI1 and CIN, because there are n people. So this is defined as CI1 times CJ1 JK overall k equals 1 to n. So the idea is that I mean, we are working over F2 and the dot product is also over F2. So it's either 0 or 1. So Ci, when I is not equal to j, Ci dot Cj is 0. And when I equals j, Ci dot Ci equals 1. These are the conditions that we have. Is that clear what the conditions translate?
No, can you, this Ci dot Ci equal to 1, I didn't get this.
This is because each club has an odd number of members. Ci dot Ci is just sum k equals 1 to n. Cik dot Cik, but Cik dot Cik is just Cik in F2, because 0 dot 0 equals 0 and 1 dot 1 equals 1. So this is just Cik, right? And this is just the sum of, this is just the number of members Ci has.
And why is the dot product of any two equal to 0?
Because this thing is 1 only if the kth person is in both the clubs. So this just counts the number of person which are in both clubs, and that is even, so 0.
Got it.
So the other thing is that now suppose for the sake of contradiction that m is greater than n. Since the dimension is n, we must have that these m vectors are linearly dependent. Since we can have at most n linearly independent vectors.
Can you repeat what are these vectors?
These vectors are the inclusion vectors of the persons, right?
No, these are dependent or independent?
These are dependent because m is greater than n, right? N is the dimension. So if you have more than n vectors, there must be some sort of linear dependence between them.
Okay.
So suppose bi are the scalars. So suppose some bi ci equals 0 for some scalars bi. I equals 1 to n.
What is BICI?
Bi is some scalar. Ci is just the vectors we define. Bi is the scalars. Bi are the scalars give the linear dependence. So this is the linear dependence that we have. So BI are not all 0. Okay. But then, since BI are not all 0, there's some j such that bj is not equal to 0, or rather bj equals 1. Okay. But in that case, you have that cj dot sigma I equals 1 to m 0 equals cj dot bici, which equals, because the dot product is distributive, bi times ci dot cj, which is just bj, which is 1, which is a contradiction. So do you follow this argument?
No. Can you
Sigma bici equals 0 by definition of the bi's. That's clear. So 0 equals cj dot 0. So since this is 0, 0 dot anything is 0. That's clear. And the dot product is distributive. So cj dot this thing is simply cj time cj dot a sum, or let's just cj dot this is something, right? C1 plus C3 is
Oh yeah, got it.
C1 dot Cj plus C3 dot Cj. Actually, I should write the Cj first because, I mean, for this dot product, it's symmetric, but not all dot products need to be symmetric. So, but whatever. And this Ci dot Cj is 0 unless I equals j. When I equals j, then Ci dot Cj equals 1. So this sum is equal to bj. So the sum is over all I equals 1 to m, I not equal to j is 0, and I equals 1 to m, and when I equals j, this is 1. So it equals bj, and bj is 1 since we selected bj to be 1 because we know that one of these bi's is not 0.
Why is the dot product not symmetric?
The dot product is symmetric, but I'm just saying that not all like bilinear forms need to be symmetric. I'll discuss that the next day, or maybe I won't discuss that. You can read about that yourself. But I mean, that's just a pedantic point. Here it's all right. Like
Okay.
this dot product is symmetric. So
and what
this
was
thing
the
equals
motive?
equals 1. So you get 0 equals 1, which is an obvious contradiction.
And what was the motivation behind this solution? Like thinking how do you motivate this linearly, this and this manipulation stuff?
So once you figure out that you need to prove that m is less than equal to, so once you have m is greater than n, the only thing you can do with more than or like n plus 1 vectors is find a linear dependence, right? And once you have a linear dependence, I guess in this particular form, this is kind of hard to motivate. There's a slightly better way of writing this in terms of matrices. So you can define this matrix A, which is, think of its columns as being persons and its rows as being the clubs. And so it's like C1. It's basically the putting the clubs one after another. So once you have this matrix, you can, I'll clear the board. Once you have this matrix, you can define A transpose A, which is a natural thing to do. Because, so the dot products, you must have understood why I took the dot products between these, right? These are precisely the translations of the conditions we have. So Ci dot Cj is precisely the number of people that are common between I and j, which is precisely 0. That's basically what the problem conditions are. So taking dot products is natural. And when you want to take a bunch of dot products between a bunch of rows, you basically create this matrix. So the entries of this matrix are C1 dot C1, C1 dot C2, C1 dot Cn, C2 dot C1, C2 dot C2, sorry, Cm, because there are m, and so on. So this is basically the dot product matrix. And we know that this is just the matrix with ones along the diagonals and zeros everywhere else. Oh, so now the point is, for matrices, there's something called rank. So this is an m cross m matrix with ones along the diagonals. This is actually the identity matrix of size m cross m. And it's well known that the rank of the identity, like it's obvious that the rank of the identity matrix is exactly the dimension. So the rank is defined to be the dimension of the output vector space. So
What is A transpose?
A transpose is when you flip the matrix on its diagonal. So A is the matrix with Ci as its rows and Pi as its column, right?
Okay, so how does A?
Actually,
so how does this give a contradiction?
I am coming to that. Actually, the way I found the matrices, I want to write A transpose, not A transpose, but it's basically the same thing.
So how is A transpose equal to identity matrix?
Because Ci dot Ci is 1 and Ci dot Cj is 0. So the entries on the diagonal are 1 and the off diagonal entries are all 0. This is because the entries are the dot products. And the rank of this matrix is m, but the rank of these matrices is at most n. Since A is an m cross n matrix, so it's known that a rank A is less than or equal to n. And these are some well-known results. I'll discuss rank tomorrow, so don't worry.
By the way, isn't this
So,
0 equal to like C2 into, this is K1, right?
That's C1. It's C2 dot C1, right? C2 dot C1 equals 0. That's because they have an even number of elements in common. So these matrices are also over F2. Because the vectors, everything is over F2. Like when working with parity, you just use F2. You don't bother with anything else. So the point is that the rank of this thing, the rank of this is at most n. But the rank of the right-hand side is precisely m. So we get that m is at most n. This is a simpler explanation.
Why is the rank of left hand side at most n, and what is the rank? Are you meaning determinant?
No, I will explain ranks tomorrow. Rank is a standard thing, but I guess you don't learn it in school or something. So explaining rank will take some time. So I'll explain it tomorrow.
Okay.
So rank is basically the size of the, you can think of it as the dimension of the vector space spanned by the columns. Okay. That's one valid definition of rank. So the rank of the vector space spanned by these vectors is obviously m. And the rank of a vector space with at most n vectors is like n-dimensional vectors is at most n, because since the dimension of the entire vector space is n, the dimension of a subspace must be at most n. And it turns out that when you multiply two matrices, the rank cannot increase. Like,
I didn't get to.
never mind, I'm going to end the lecture now. I'll talk about all that tomorrow or in Discord if you want.
Okay, thanks for the class.
Yeah, sure.
You are leaving or we can discuss right now?
Yeah, I'll discuss most of this tomorrow. Like, I will discuss ranks and matrices tomorrow. I haven't even properly talked about matrices today, so I'll discuss matrices tomorrow. And I think you can try some of the homework problems. I'll tell you which problems to try. I don't think you will be able to solve all of